Hello everyone, this is Dr. Hopkins narrating the next video in our series. Today we're going to discuss phase changes and relate it to the chemical potential, which we learned in the last video. Alright, so for a one component, what I mean by one component is one substance that can have any number of phases. So it could be multiple solid phases, it could be liquid, or it could be gas. So if we write out the Gibbs free energy, the differential Gibbs free energy. We learned this the last time, right? We have VDP, SDT. These are per molar, just to remove to make it an intensive property. And then we have chemical potential and the change in the number of moles of each. Now we also know that we can expand the differential equation in terms of partial derivatives. So we have these, which means that our partial derivative with respect to G, and actually the partial derivative with respect to mu, within a particular phase, as you change pressure, is the molar volume of that particular phase. So for each individual phase, we have this partial derivative that's the molar volume or minus the molar entropy. Okay, so we're going to use that to describe phase changes. So we know, based on the last video and based on our understanding of spontaneity, that systems will adapt to minimize the Gibbs free energy, which means it's going to minimize the chemical potentials of the substances involved. And so if you have something that has two phases, one of them has a lower chemical potential than the other, then what's going to happen? You're going to get mass transport from the phase with the higher chemical potential to the phase with the lower chemical potential. Right, so basically, if it's solid to liquid, you're going to have it melt. Once it reaches equilibrium, there's no difference. If we have both solid and liquid at equilibrium, they have identical chemical potentials. And we can show that mathematically with this generic two-phase system, alpha and beta. We have our two differential equations. And then if we want to know the total Gibbs free energy, we just sum them up, their state functions, and then we end up with this. Okay, so then at equilibrium, we know that we're not going to vary temperature and pressure, because if you vary temperature and pressure, you're not at equilibrium anymore. It will readjust again. And so our Gibbs free energy is this sum, and it's also equal to 0 because it's at equilibrium. And so that means that the chemical potential of alpha times the change in moles, chemical potential of beta times the change in moles are equal. And we do know that we have to have conservation of mass. We start out with X mass of the substance, some of it's solid, some of it's liquid, but if you change from liquid to solid, you might be gaining solid, but you're losing the same amount of liquid, which means that these chemical potentials have to be equal. And now when we think about phase changes, we always think about the temperature. So you identify the melting point and the boiling point of a particular substance. So if we go back to our first slide, we identified these partial derivative, which is basically just a slope, right? So if we were to plot chemical potential versus temperature, the slope would be minus the molar entropy of that particular phase. Now we know, based on third law, molar entropy has to be greater than or equal to 0. It can't be negative, right? It always goes up. And that would be for any phase, so solid, liquid, gas. So that means that our slope, if we plot mu versus t, has to be negative. It cannot be positive. It's impossible. And then if we just use intuition, or even if we just thought about third law entropies as they go up in temperature, as we go up the various phases, the entropy increases. But just thinking about disorder for a moment, I mean, the disorder of a gas is highest, and it's actually much, much higher than the liquid or the solid, because we're now assuming no intermolecular interactions, right? And then we would also assume the entropy of the liquid is greater than the solid, right? Because there's more freedom of motion in the liquid than in solid. So from a disorder standpoint, this should make sense. So if we were to take our one component system and plot out the potentials, the chemical potentials of each of the three phases. We're just going to restrict to one solid phase. We would have a solid, a liquid, and a gas. All of them have negative slope, and the solid slope is less than the liquid slope is much less than the gas slope. So that's what that's representing. Now if we wanted to read this plot, we have temperature. So let's start at a low temperature. We're always in the phase that has the lowest chemical potential. So if we extrapolate these two out, they're much higher than the solid. So at low temperature, the solid has the lowest chemical potential. We start increasing, we go up, still the lowest, till we get to this point where it crosses with the solid and liquid. At that point, the chemical potentials are identical. We're going to have equilibrium and a phase transition. We're going to have both phases. And if we go a little higher in temperature, past that phase transition, the melting point at that point, then the lowest chemical potential is the liquid. And so we're now in pure liquid phase. All the solid will melt because the chemical potential of the liquid is lower. And then we increase that, it's lower, lower, lower until we get to this point where they're equal. That's the boiling point where we have liquid and gas in equilibrium. We go a little higher in temperature and the gas now has the lowest chemical potential. So that's the phase we will see. So that's basically the thermodynamic driving force for phase transitions, temperature dependence. If you have something that's sublime, so I just described the classic melting and then boiling, that means the solid gas chemical potential lines will cross before it crosses the liquid so that you get a sublimation, basically. Now the pressure dependence, we can once again go back to our Gibbs free energy equation on our partial derivatives. And remember the partial derivative with respect to pressure, right? So we're looking at how it changes as we vary pressure. It's the molar volume. Now we know the molar volume has to be greater than zero. There's no negative volume. So that means that anytime we raise the pressure, we're going to raise the chemical potential. Okay? So it doesn't matter what the substance is, we raise the pressure, we raise the chemical potential. Now the effect may be larger in some others, and if we think about it just like we did with the entropy, let's kind of reason through these molar volumes. And there's one that's really easy to decide, because the molar volume of a gas, it's much larger than either one of the other two because it expands to fill the volume of the container. But then if we want to compare liquid versus solid, we have to consider what the substance is. And the classic example is water. Water is one where the molar volume of the solid is actually larger than the molar volume of the liquid. So we have ice that floats rather than sinks. And so you can write this chemical potential versus temperature. We'll keep it on the same kind of diagram, and we have our lowest pressures here, so solid, liquid, gas. These would be our phase transitions. I don't extrapolate all the way out to where the actual boiling point would be. As you raise the pressure, the chemical potential goes up. So these three lines represent the chemical potentials at the various pressures for solid, liquid, and gas. And so if you want to know what's the effect on pressure, you actually have to go through and figure out what these chemical potentials are so that you know how they cross. So if we look at, let's look at solid to liquid. So solid to liquid, the first one, this would be the melting point at the lowest pressure. And then as you go, if you increase pressure, the melting point increases to this temperature. I didn't drop it down, but you can see where this crosses, this is a little higher. So as pressure increases, the melting point is actually increasing in temperature because of the way the chemical potential plots are changing in terms of their slope. So it's a little less clear in terms of the pressure dependence. You have to kind of look at each individual plot, but you can reason through how phase changes change with changes in pressure. Until next time.